Thanks, Andrew. Hello, everyone. Welcome to another edition of 8KB Conference. It is such a great initiative by Mark, Andrew, and Anthony, and truly excited and honored to be part of this conference and kickstarting this in the year 2021 with the first session. So welcome once again. Special thanks to Ben Weisman for helping me moderate this session. Basically, the organizers did not give him much choice, so he had to go with my session. My name is Amit Bansal, and I'm going to try melting your brain with SQL Server memory internals and troubleshooting for the next 60 minutes or so, maybe 75 minutes, including Q&A. So let's get started. You can find all the event and session resources, not only 8KB, but even past sessions that I've done on this URL, bit.ly/SQL Maestros resources. We have a small YouTube channel as well. YouTube is not small, but the channel is small, which is youtube.com/SQL Maestros. And you can connect with me here, bit.ly/connect with AB. I'm on Twitter, _Bansal, in case you wish to tweet. Quickly about my work, some credentials from Microsoft, which is I'm an MCM for SQL Server, MVP for a couple of years, also regional director. I work for SQL Maestros, which is my full-time job, consulting, training, video courses, and stuff. And on community front, I work with Data Platform Geeks, SQL Server Geeks, and Data Platform Summit. That's about myself. Before we begin, quick warning. There are going to be a lot of demos in this session. Do not try these demos on your production boxes or on your stable machines. You may want to play around with all the scripts that I'm going to share on a VM, a throwaway VM or something like that. SQL Server memory is convoluted, and I say this with a lot of responsibility because I have been working and trying to investigate about SQL Server memory over so many years, and I know so many people from the community have been doing that. And what we have realized that it is, of course, complicated if you dive more deep into memory and trying to figure out every arithmetic, every number that you see flying in the DMVs is really not quite practical. So the warning here is that we'll go deep and try to satisfy your intellectual curiosity. But at the same time, we got to be practical. So what I have done in this session, in these 75 minutes, I'm going to definitely cover SQL Server architecture, the memory portion up to level 300, 400, and then focus a lot on practical demos, because that is what you really want. You want to take away something that you can apply in your production, just not theoretical stuff. So that's what I am going to be doing. So first up, we will not talk about all the architectural stuff. SQL Server memory internals is huge. It is absolutely very huge. All the possible memory scenarios. There could be a lot of different scenarios, internal memory pressures and external memory pressure. We are not going to cover everything, but I'm going to cover a few of them along with demos. And of course, bunch of perf mount counters and DMVs. And of course, these 75 minutes is not going to be enough to cover all of them. We'll cover important ones and important attributes from those DMVs. And of course, the Microsoft documentation is the place where you should go to figure out more scripts. What are we going to talk about? We're going to quickly cover NUMA, because NUMA knowledge is important before we dive deep into SQL Server memory architecture. Then, of course, I will cover, I have a slide where I have a lot of details about SQL Server memory architecture, and I'm going to give you a pictorial representation. We will look into memory usage tracking. How can you track where memory is being consumed inside SQL Server? That is a very common question that I see across all forums, that SQL Server is hitting up all the memory. It has hogged up all the memory that has been allocated to it. Where is it being allocated? And we'll try to figure that out. We're going to look at least 2 or 3 memory pressure examples. So without really devastating my VM, I'm going to create out of memory exceptions, and we will see how we can troubleshoot them. And of course, loads of demos. So what are your takeaways? Your takeaways are going to be better understanding of how SQL Server memory works and how to approach troubleshooting. Simple stuff. And we will do level 300, 400 stuff in a simplified way. So let's get started. And first, as we get started, let's get NUMA out of our way. Back in the days when we had symmetric multiprocessing systems, if you look at the diagram there, the illustration, we had a single memory controller. And when you are scaling beyond 2 to 4 CPUs, CPUs need memory. And when you had a single memory controller, all of these CPUs competed for this memory controller because they all needed memory. So they used to be huge amount of congestion at the memory controller. To elevate this contention at the memory controller, we have this architecture which is called as non-uniform memory access or non-uniform memory architecture, where the memory at physical layer, at the hardware level, is divided into NUMA pods. Yes, the word is pods or NUMA groups in simplified way. So if you look at the architecture here, there is a simple illustration of, let's say, a 32 GB box being divided into 16 GB memory NUMA pod 1 and another 16 GB memory controller 2. And then based on these NUMA pods, even the CPUs are bifurcated by NUMA. So it's just not the memory bifurcation, it is also the CPU bifurcation. And remember, this is not logical, this is physical. Now, CPUs in a specific pod have access to their own memory controller. So NUMA node, and we also call this as node, to be technically more clear. So in this diagram, you can see there is NUMA node 0 and NUMA node 1. So CPUs in node 0, let's say CPU 0 to 3, will access the memory controller of NUMA node 0, and CPU 4 to 7 will access the memory controller of NUMA node 1. With this, what happens is NUMA at bottom line is what is NUMA really helping with? Faster access to memory for the CPUs. At the core, this is what NUMA really helps with. And you can, of course, reconfigure it using soft NUMA, etc., which is beyond the scope of this session, but just calling this out. Now, what are the guiding principles about SQL Server memory architecture? First, dynamic acquisition and freeing of memory, mostly automatic. Now, SQL Server memory is designed to be automatic. You have a few knobs and switches, but mostly it is managed automatic, which is as you keep running workloads, as SQL Server is accepting more connections, requests, more queries, SQL Server will keep asking Windows for more and more memory. This is dynamic allocation. We are going to dive deep into this and explore more. But yeah, dynamic allocation is going to happen. And when at certain point, let's say if Windows is short on memory, it sends low memory notification to SQL Server, and SQL Server may start releasing memory back to Windows. So if you can see, this is dynamic allocation and dynamic deallocation, and mostly managed automatic. But you do have a few switches like min memory, max memory, and a couple of more settings that that can help you to control a bit, but then at very basic level. The second guiding principle is minimize physical I/O and maximize buffer pool. Buffer pool is one of the most important memory consumers in SQL Server. It has only one job, which is to ensure that there is enough data cache to load the data pages from disk into memory. We all know that physical I/O turns out to be quite expensive, and SQL Server will ensure that physical I/O is least so that everything is there in memory as much as, and that's one of the reasons why you see when you allocate more and more memory to SQL Server, it just eats up everything. And if you run some of the scripts that I'm going to show you, you will see that in most cases, buffer pool is one of the largest consumers of memory. So the objective of SQL Server memory controller here is to minimize physical I/O. But at the same time, if you look at point 3, to keep a check on buffer pool size to avoid system-wide memory pressure. So point 3 and point 2 is kind of contradictory in nature. This is where SQL Server tries to strike a fine balance between ensuring that buffer pool size is good enough, yet not so large so that it causes or puts pressure on other memory consumers. Remember, inside SQL Server, there are many components that ask for memory, and they do that via clerks. We will talk about that. And because buffer pool is one of the largest consumers, SQL Server needs to ensure that fair amount of memory is given to all other consumers and clerks. Lock pages in memory. You have heard that this is one of the best practices to kind of turn it on so that you run in locked pages memory model of SQL Server. But that was really a lot required in 32-bit systems. Today, I'm going to focus solely on 64-bit system. And in 64-bit, you may not turn it on because in 64-bit systems, by default, Windows does ensure that the memory addresses of SQL Server are locked in pages. But if you see those errors coming out in error logs, a significant part of SQL Server memory has been phased out, that typical popular message, then you may want to turn this on, lock pages in memory. Min and max memory settings has quite a bit of myths around. And let me just take a moment to quickly demystify a few things. First about max. Max memory starting from SQL Server 2012 onwards represents almost the max memory of SQL Server. Back in the days prior to SQL Server 2012, it used to represent only the max memory for the buffer pool. But then from 2012 onwards, there have been quite a few changes to SQL Server memory architecture and the memory controller. And max now means max, almost. I say almost because there are certain components that still are outside the purview of so-called SQL Server Max, which is they do direct Windows allocations via direct calls to VAS. For example, the thread stack, for example, common language runtime. And let's say if you have loaded a DLL in SQL Server process address space, then it is not going to come under the purview of Max. It is going to be a direct Windows allocation. So be careful about these things with max memory settings. And of course, min means that once you set up something with min, it is expected that SQL Server memory consumption will not go below it. With max also, I have seen questions in the forum where people say, I have set max to 32 GB for SQL Server, but it still eats up 34, 35, 36 GB. Well, that is a normal behavior. SQL Server can try to overcome it if required, but then it trims down or scales down below the max whenever there is an opportunity. So that's a normal behavior. Buffer pool, the caches and query workspace memory. These are some of the most important consumers. You know, buffer pool for the data pages. There are different caches in clerks. For example, your cache for the plans, and in plans also you have object plans, you have ad hoc plans, and you have bound trees. So there are a bunch of these caches, and something that is known quite less, which is query workspace memory. When you run your queries, they also need memory. I'm not talking about the session memory. I'm talking about your queries when they do expensive operations like sorting or hashing or parallel queries, they require extra memory. So that memory is called as query workspace memory. Today, we're going to talk a bit about that as well. Memory is bifurcated by NUMA, which means that when you have multiple nodes on your system, on your hardware, even SQL Server memory is divided by those nodes. Simple example, if your hardware has 4 nodes, NUMA node 0, 1, 2, and 3, even SQL Server memory will see SQL Server, the SQL OS layer is going to create 4 NUMA nodes internally. And the memory that SQL Server has will also be divided with these NUMA nodes, which means you're going to have 4 lazy writers, 4 resource monitors, 1 clerk for each node, which means you will have 4 clerks for buffer pool. Everything is going to be bifurcated by NUMA. You can reconfigure this using soft NUMA. So you may keep that in mind. Memory pressures are of 2 types, internal and external. And don't try to compute every number. You will never get it because there's so many different flying numbers, committed, reserved, and trying to, if you run DBCC memory status, you will see all sorts of numbers. It just doesn't make so much sense. What is important is the practical way of troubleshooting SQL Server memory pressure. Last but not the least, when speakers talk about SQL Server memory, they sometimes say things that are wrong and their demos might not work. That is one of the guiding principles of this session. So welcome to the dungeon, SQL Server memory. And I say SQL Server memory equals to CCC, complicated, convoluted, and confusing. All right, so let's look at the architecture of SQL Server memory with this illustration. On the left-hand side, you have the physical RAM of the box, right? The Windows operating system. You can track how much RAM is there on the box or on the VM by using DMV, SysDM OS process memory, and SysDM OS sys memory. Then you have the NUMA nodes. Now, this is still at Windows level. We have not talked about SQL Server at all. And as I said in the beginning, assuming, and today most of your systems do have NUMA implemented at the hardware level. So let's say in this example, in this illustration, there are 4 NUMA nodes there. You can track these nodes using SysDM OS nodes. So what happens is when SQL Server EXE, the database engine, boots up, it reads the hardware information and it reads that there are 4 NUMA nodes, and SQL OS, the mini operating system inside SQL Server engine, will create one NUMA node, a logical NUMA node per physical NUMA node that is there on the system. And you can track that using sysdm OS nodes. Now that's very basic about the Windows physical RAM and the NUMA node. One thing, just to digress, when you really want to dive deeper into SQL Server memory, I spent quite a bit of time reading about Windows memory first. The concept about, back in the days with 32 bits, AWE /3G, boot.ini, and the virtual address space, the concept of VAS and the kernel allocation, the user mode, the kernel mode. So there's a lot of this background that might be very helpful if you really want to read a lot more about SQL Server memory. Anyway, let's proceed forward. And now comes the SQL Server portion. So as I said, when SQL Server boots up, it reads the NUMA information and it creates the memory node. So if you can see in the illustration, we have 4 memory nodes, 0, 1, 2, and 3. And you can track all the memory nodes using the DIM OS memory nodes. Remember, there's a difference between DIM OS nodes and DIM OS memory nodes, because OS nodes will give you OS level information and OS memory nodes will give you memory related information from SQL Server's perspective. That's important to note. Now, what happens is when SQL Server consumers, when I say consumers, I mean buffer pool or the plan cache or the query workspace, when they need memory, allocations are done via these nodes. They don't talk to Windows directly. And nodes in turn call the allocators, which we call as memory allocators, via Windows APIs. And there are base allocators and structured allocators. Now, the end of the day, these are all Win32 APIs, and depending on how the allocation is being asked for, is the allocation happening in huge blocks or is it happening in fragments, the respective Win32 API is going to be called. In most cases, it is virtual alloc that happens because the allocation happens via the virtual address space. So these base allocators and structured allocators are being called. If you're really interested, shoot a WinDBG and just try to load up a big table, and you can see that the virtual alloc and virtual alloc X is going to be called in Win32 in WinDBG tool. Now let's move forward. I have talked about the OS memory nodes from a SQL Server perspective. And now as we gradually move into SQL Server memory architecture, it's fair and wise to say that SQL Server memory architecture is divided into 3 different layers, or it's like a 3-layered architecture. At the topmost layer, you have memory nodes that are talking to Windows directly via these allocators. And at the next layer, you have memory clerks. And at the bottommost layer, you have memory objects. You can track all the clerks using DIM OS memory clerks and all the objects using sysdm OS memory objects. Let's talk about the clerks. Clerks by far are the most important piece of information in this entire diagram as far as I'm concerned, because I use DIM OS memory clerks so often to track memory consumption. Now, what are memory clerks? As mentioned before, SQL Server has memory consumers inside it. So like buffer pool, plan cache, query workspace, right? The parse tree, what we call as the boundaries, lock manager, the session memory, the connections. Each and every consumer needs memory. And what SQL Server architecture here does is there is a clerk for each of these consumers. So when these consumers need memory, they talk to their clerks, and clerks in turn will request memory via the nodes. So if there is one question that is there in your mind, can I track SQL Server memory consumption component-wise or consumer-wise? The answer is clerks. In the upcoming demos, you will see that I'm going to use this DIM OS clerks quite frequently to see where is my memory being consumed, not my memory, SQL Server's memory. Then comes the, okay, so one more part of the diagram there, general, object store, user store, and cache store. Typically, clerks are divided into these 4 categories: general, object store, user store, and cache store. What's important for us to know is about cache store, and I'll come to cache stores in a moment. Let's talk about memory objects. In the three-layered architecture at the lowest level, you have memory objects. Memory objects are simply memory allocations that are being done via the clerks. So in simple words, when clerks have to allocate memory, they create hundreds and thousands of memory objects. If you look at some of those comments there, memory objects could be variable size, it could be mark shrink type, or it could be fixed size, which means that memory objects can grow as needed, or they could be fixed in nature. For example, 8K memory object, and when you need, let's say, 800 MB for something, you will have those many memory objects being created. So memory objects are the most granular level of information that you can get from SQL Server memory internals. Now, do we really need to track memory objects to troubleshoot memory? Sometimes, and that is why in one of the examples today, I will show you that clerks did not give me enough information about where the memory was being consumed, and then I had to go to memory objects, and we can figure that out. You can track all the memory objects using sysdmos memory objects. Now let's go back to the cache store. So when you talk about the clerks, there are some types of clerks that are called as caches, and this is something that you know. I've named the popular cache stores out there, like object plans, ad hoc plans, boundaries, and extended procs. And those are the names, cache store underscore obj cp. Now, when allocations are required by these cache stores, there's another part of SQL Server memory architecture, which is called as the brokering system. And broker, as the name says, does the job of negotiating between these cache stores and between these clerks. It's not like a clerk wants memory, so it asks for, let's say, 20 GB for something, and SQL Server will just allocate it. No, the brokering system actually handles the demand supply algorithm and is responsible to ensure that how much memory is being allocated to a specific clerk, and if more memory is required, can it pressurize other clerks to release some memory, so on and so forth. So that is done by the memory brokers. Further deep, if we go into the cache store, the architecture, cache means there are cache entries. Let's take example of plan cache. And in a plan cache today, if you go to your production box and if you simply see how many plans you have using dim exec cache plans, you will see thousands of plans in the plan cache. These are called as cache entries. And what SQL Server really has to do is more cache objects keep coming in, and the old ones need to get flushed out. There is an algorithm which we call as the clock hand system, which does that. You may get more low-level information about cache stores and cache entries using some of those DMVs, demos, memory cache counters, cache entries, and cache plans. And then there is this all on the top right corner resource monitor, which is keeping a bird's eye view on what's really happening and sends memory notifications to Windows. You can track whether SQL Server is low on physical memory, so on and so forth. And you can get some information in this DMV sysdmos ring buffers. So that helps a bit. Now, when all this while we have been talking about SQL Server memory consumers asking for memory, and the memory that they get is from the SQL Server exe, the SQL Server process space. There are certain allocations that happen directly with Windows. Those are called as direct Windows allocations, or DWA. Let's take an example. You have created a DLL, for example, and you load that DLL in SQL Server process space. And let's say if that DLL is asking for memory, that is going to be a direct Windows allocation via the virtual address space. It's not going to be via this architecture of objects, clerks, and nodes. So just to call that out, and in the demo, I will show you a small example of that as well. Memory models. Well, all these are finer and granular details. At the topmost level, you have three memory models in which SQL Server can run: conventional, locked, and large. If you have a vanilla installation of SQL Server, it's a conventional model. You're not making any changes whatsoever. If you turn on locked pages in memory, if you turn that option on via the group policy, etc., and you turn on the user right assignments for locked pages in memory, then that becomes the locked memory model. And there is another memory model which is called as large memory model, that is to support Windows large page option. Not so frequently used, but you may read more about that on Microsoft documentation. You have to turn on trace flag 834. Your system needs to have more than 8 GB of physical RAM and has to have enterprise edition, etc. That will enable large memory option to take advantage of the Windows large mem option. But then it does have some side effects, because when SQL Server, let's say, boots up in large memory model, it's going to reserve all the memory upfront. Remember, we talked about the dynamic allocation and deallocation. That's not going to happen. It will reserve all the memory upfront, because mostly in, let's say, in cases where I've seen SQL Server escalation engineers recommending that, because maybe there are, memory intensive queries and huge plans that are running that may be helped with contiguous memory. When you need contiguous memory, you do need contiguous space, and that SQL Server can get using the large memory option. Well, with this, we come to an end of this illustration, and hope it was useful to just get a fair bit of idea about what SQL Server memory architecture looks like. It's time to jump to demos, and let me switch over to the VM. And maybe someone from the moderator or organizing team can confirm if the VM is showing up.
Yes, it is. And while I get you here, Amit, I got one quick question from the audience just in between. Will you also be sharing your scripts or only the slides?
Of course, I would be sharing all the scripts.
Okay, perfect.
Yeah, and in fact, as the session ends on the last slide, I have the URL, and it's also available with 8 KB GitHub. I just made the organizers a few minutes back because I was making last minute changes.
Excellent. All right. Thank you.
Thank you, Ben. So friends, let's get started with the demos, and remember the guiding principle, right? When speakers talk about SQL Server memory, demos may not work, right? So with that guiding principle, let's begin with the demos. This is what the 8 KB Jan 2021 folder looks like. And when you get the resources, you will have a similar structure. So I'm going to use this one for some internals demos. Then I'm going to use 3 examples of out of memory exception, out of which the first and second will really cause an OOM if the demos work. And the last one, 3_OM, will not cause, because that makes my VM unstable for some reason. So I changed that a bit and a few more things. So there is a perf mount counter already configured with some counters there, some objects. So we will keep coming back to perf mount and observe total server memory, target server memory. I might occasionally look into the workspace stuff, and we can see page life expectancy, etc. Now, things to note here before we begin the demo. Look at buffer cache hit ratio. Very good, sitting at 100%. Look at PLE, 5771, pretty neat, and it's increasing. If you observe this, it will increase by 1 every second. So 803, 804, 805, so on and so forth. Because when there is memory pressure, you will see that they all reset back to 0. Talking about PLE, I mean, just to digress a bit, there are DMVs that give a whole lot of information, and we may sometimes not go and look into PLE, but I just brought this up in the perf mount counter because some of you might still be using many of these counters. Total server memory is 653 right now here, you can see. And let's go and look at the taskbar. If you see in the taskbar, again, about 650 MB is what SQL Server process is using. Now, I have opened up the task manager here and the perf mount counter. You can see the numbers up there. They're matching 650. And if you look at my helpers.sql and let's execute dimOS process memory, you can see about 700 MB being used there in the DMV. Now, the reason why I have all the 3 tools open, and these are native mechanisms of extracting memory information. You are most welcome to use a lot of different third-party tools out there, but I would like to stick to these 3 for the time being. And the reason why I have all 3 open is to show you that DMVs are the most authentic way of getting memory information or SQL Server internal information, and that will be evident to you in a while. Now, when you look at this, of course, I'm not using large page allocations or log pages. This is just a vanilla installation of SQL Server, and there is VAS reserved and VAS committed. Now, I'm trying to understand about virtual address space concept is beyond the scope of this session. That is really like Memory 101. So I would really invite you to read a little more about Windows memory, and these concepts might get cleared off. So the memory is what it looks like, 692. Now let's go to the first file, 1_memory, and let's look at first layer, the nodes. Now, DIM OS nodes. On my laptop right now, there is no physical NUMA configuration. So the default node is node 0. So which means that even if you do not have NUMA configured, you still have the default node 0, and node 64 is for DAC. Now, this is node information. This is very low level information about the physical node itself. But if you want at node level information about memory, which is memory nodes. So if you look at the DMV DIM OS memory nodes, let's execute this. And you can see that target is about 7 GB. So that's the target memory allocated to this specific node. And if you look at the target server memory, that's also matching up with what you see in the DMV. So that's target server memory. The reserved GB is 25 and committed is about 638. Now VAS committed is similar to what you see in the total SQL Server memory consumption. So committed can never go below the actual consumption, and committed sometimes is slightly higher. Reserved is about 25 GB. Where that number comes from, let's discuss that some other time. So we talked about memory nodes, then you have the memory clerks. I will jump to the helpers section here, and let's go and look at the clerks. Now, as I said, clerks are really important. They tell you how much memory is being consumed by each component inside SQL Server. Remember, most components have their own clerks, but some components do not have their clerks, and they get their memory allocation via the general clerk. And we'll see that in the example. Now, if you look at the clerks here, you can see PHDR, which is for boundaries, the SQL plans for the ad hoc plans. These are all consuming about 70 MB, 68 MB, 60 MB, so on and so forth. Very limited use. It's a vanilla SQL Server installation, and I've just started it. So the memory consumptions are very low. Okay, so let's put this down and go back to objects. Now, if you look at memory objects, if you are running this DMV for the first time, all of this is not going to make sense to you. What are these object addresses? What are the different types of objects and the memory consumption and so on and so forth? But now when I show you the demo, and you can see fixed memory objects, which mean they're always 8K, so on and so forth. So we are going to match this up with clerks using memory allocators, and then these numbers and these concepts will make sense. Now let's get started with the demos and try to understand the basic memory consumption. First up, the buffer pool. So if you see, I am trying to compute how much amount of memory is being consumed by the buffer pool, and I am filtering on my clerk type memory clerk buffer pool. So let's go and execute this, and you can see the buffer pool is only consuming about 99 MB, close to 100 MB. Now remember, starting from 2012 onwards, as I said before, buffer pool's only job is to ensure that there is a healthy data cache that it maintains, which is creating a buffer space for the data pages to be loaded from disk to memory. Now, 99 MB, where is this 99 MB being used? So using one of the DMV's DMOS buffer descriptors, you can actually get a bifurcation of all the databases and how much memory are they consuming, in sense, how much memory is being consumed by their data pages. This kind of work queries are important because buffer pool tends to be one of the largest memory consumers, and it runs into hundreds of GBs. And that is the point where you may want to find out that out of hundreds of databases that you have on your production box, which database or which set of tables are consuming maximum memory. When I say tables consuming maximum memory, I mean the data pages for those tables are being loaded into memory. At this point, you can see that everything is sitting quite quiescent. You have the hidden resource DB with 23 MB, but nothing much up. Now, not only that much, for example, AdventureWorks 2016, let's say, let's take this database as an example. So for AdventureWorks 2016, which tables are consuming maximum amount of memory, or in other words, their data pages in the memory. And you can see, again, quite quiescent. Now let's run some queries. So in AdventureWorks, I'm just simply going to run select star from sales order header and sales order detail. The moment you fire these queries, the workloads, data pages are being read from disk into memory. And if we go back and try to first find out memory consumption database wise, you can see AdventureWorks 2016 pops up on top 3 and is consuming about 20 MB. And inside AdventureWorks 2016, which tables have their data pages in memory, in physical memory, that is about 9 MB and 5 MB for these two tables, sales order detail and sales order header. To take this one step further, if I have a big table here called transactions. So let's just run select star from transactions. And this has a few million rows. And as it loads pages from disk to memory, which means physical IO is happening, let's go and look into the helper. So there we execute, and you can keep an eye on the memory use, which is right now 796. And what I have done here is I am looking at the total physical memory consumption, and I'm also looking at the clerk sort by pages KB descending. So you can see buffer pool clerk comes on top right now, pages MB. So let's execute this once more. Keep an eye. So now we are consuming close to 900 MB total physical usage, and buffer pool is consuming about 255 MB. And you can see memory consumption keeps shooting up, keeps increasing as more and more data pages are being read from disk into memory. This helps because, as I said in forums, I see most questions, where is my memory being consumed? And I can see that cache stores, the cache stores for my plans, for my execution plans are quite low. It's the buffer pool that is turning out to be the largest memory consumer. Let's go and stop this for the time being and close this. And if we look into this bifurcation again, first let's look at the databases, and you will see now AdventureWorks 2016 should shoot up right on the top. This database has its pages worth 375 MB into the buffer pool. And which table, let's look at this, and you will see that transactions is what I ran, which is consuming about 355 MB out there. Sometimes a good indication of could they be good candidates for in-memory OLTP? Well, there are many other factors like latch contention, etc., that you need to see, but just not the amount of memory. Now let's close down. Just a second. All right, sorry for the interruption. And okay, what next we have? Okay, let's go one level down now and understand the memory clerks in more details. Now, we talked about the 3-layer memory architecture. So we looked into nodes, we looked into buffer pool as one of the clerks. So I will dive a little more deep now. There is a memory clerk called cache stored PHDR. Okay, this is for the bound trees. And if you can see, the pages KB is 85928. So keep that number in mind, 85928 kilobytes is what is being consumed. And if we look at, now I'm going to correlate memory clerks and memory objects. So if memory clerks cache stored PHDR is consuming 85928, what are the different memory objects this particular clerk has created? And if I add up the size of all the memory objects created by clerk, I should expect probably 85928. So what I've done here is I am joining memory objects and memory clerks using the allocator address, which is the common attribute in both the DMVs. And I'm filtering on B type cache stored PHDR. Let's go and execute this. And you can see mem obj parse, and you can see the pages in bytes. Now remember, each object there, so we can see about 487. This is nothing in production boxes. This number will be very high. So mem obj parse is the object that is created by the clerk cache stored PHDR, and looks like this is a fixed sized object. Yes, it is page in size in bytes, as you can see, 8192. And if we add all this up now, if we sum up all the memobj parse object, what does it come up to? 85872. So it's not 85928, it is 85872, which means there could be one root object. So let's just go and run this once more. And let's look up for the root object. There you go. This is our root object, as you can see. And then the rest of the memobj parse object. So what I can do is take up pages in bytes, this one here, and add up here, and then sum up all the pages in bytes, including this additional, and execute. And can I see 85976? So there is something that might be missing. Well, this is what we are trying to dive is internals into SQL Server memory. So let me just check one more time. Is my pages in bytes? Okay, that's there. It's 85976. That's correct, not 928, which means it increased a bit. And when I add this up here with all the memory objects, you get 85976. So a quick summary, what did I try to do? I am trying to dive deep into the nodes, the clerks, and the memory objects. Remember, what are memory objects? Memory objects are memory allocations via clerks, which means the amount of memory the clerk is asking from the node, it breaks that memory consumption into these number of memory objects. So all I was trying to do is for cache store PHDR, which is a memory clerk, I'm trying to find out all the objects created by it, adding up their sizes and seeing is it equivalent to the clerk size. That's all. Okay. So that's a lot about the memory clerks. Now let's look into the direct Windows allocation. And we talked about direct Windows allocation. So let's open up DLL execution. Ben, I had a small interruption. Can I just have a minute, please?
Yes.
Sorry, folks, just a short break for a minute, please.
This is where I awkwardly interrupt and remind people to please, if you have any questions, put them in the Zoom Q&A. If you have feedback after the session, please go to 8kb.online/feedback. As we've already posted a couple of times and we'll keep posting over the course of this day, all the materials from all the 5 sessions will end up on the 8kb GitHub, and the recordings will end up on YouTube, though I understand that's happening on YouTube depends on, may I quote here, Mark getting his stuff together? Is that what you said, Andrew?
Yeah, when Mark decides to get his act together and do some video editing.
My act is together just fine.
I'm just saying, Anthony was saying in the chat that being interrupted while presenting from home is such a 2021, what's the word? Occurrence?
On brand. Yeah.
On brand, that's the word, yeah.
Yeah, I have the same thing. My printer is in my office here, and the kids are at home doing online school. So periodically, I'll be on a video, and I'll just walk in and grab a print job.
You're back, Amit. No worries.
Yes.
All right. Good luck,
sir. So
back over to you.
Probably you and all the attendees should know. So I'm presenting this from a new office of mine, and I posted the picture some time back. And this is my first session from the new office, and the security guard came that you're sitting up late. Is everything all right? So probably that is what I've put the securities away. Now let's continue. Just have a drink of water. All right, friends. So we talked about the memory clerk allocations and memory objects. Let's look into direct Windows allocation. So on the slide, if you recollect, I talked about that direct Windows allocations do not go via this 3-layered architecture. So I have a DLL file here called heap_leak.dll. So let's go and register this first. I'm executing in the master database. Okay, that's interesting. So let's go and do this. And we execute this, and this is done. And now let's open up the helpers and we'll execute the helpers and see where do we stand with memory. So what you can see here is SQL Server memory currently in use is about 1100 MB, and we have the buffer pool 376, 71 for PHDR, so on and so forth. Keep these numbers in mind, and buffer pool is about 479 there, and we have these are the cache stores there. Now, what I'm going to do is the DLL, I'm going to execute the DLL, which is going to consume some amount of memory. And you will see that this is not happening via the 3-layered architecture, which means you will not see consumption from any clerk or any memory object. At the same time, let's look up at these numbers. Total server memory is also about 1055 MB there, about 1000 MB. And if you look at the task manager there, it's also at about 1055. So all good there. Let's get started and let's go and execute the DLL. We will execute this DLL, let's say about 100 times. And mind you, the number is 1086 there. Let's go and execute heap lake DLL about 100 sites. So 100 executions have happened. Let's go and look at the memory consumption now. You can see that SQL Server memory consumption has increased by a good deal of about 300 MB there. Yes. Yeah. 1491. And look at the clerks, 376, 71. This is what the clerk status was before the execution. Same with the cache stores. They all remain the same, and the clerks. Now, if you go and look into the task bar there, SQL Server EXE, it is about 1471. So task manager shows up the direct Windows allocation. But when you go into the perfmon counter, look at this. This is going to be strange. Total server memory does not show up direct Windows allocation. And this is where I keep advising folks that while these counters make a lot of sense and you should definitely keep monitoring them, be aware that some of these counters do not show direct Windows allocation. But of course, the DMVs definitely show every bit of memory information. And that's what we tried to do with this direct Windows allocation. So let's close this one. Hope this was clear. Well, with internals, we did talk about, let's take another example of query workspace memory. So we talked about the clerks, the memory objects, direct Windows allocations. And now let's see the clerks. Now here is a simple query, and which is trying to do a cross join and multi-level sort, which means sort is going to be slightly expensive here. And when I execute this, while it is running, we go to the helpers and execute this. You will see now that memory clerk SQL reservations comes on top, and it's consuming about close to 700 to 800 megabytes of space. Now this is interesting. Now you can see suddenly SQL reservation shoots up on top much more than buffer pool. And when you stop this workload and go to the helper and execute this again, you can see SQL reservation just vanishes away. So this is like clerk allocation and deallocation happening very dynamically. This is something important to keep in mind, that while we troubleshoot SQL Server memory, there's nowhere this information is recorded, which means I can't go back in time and find out which clerk consumed what amount of memory. And this is where it gets a bit tricky to troubleshoot SQL Server memory. And that is the reason why what I typically do, and it's just an advice from me, we create baseline. In the baseline database, we have these memory tables, and periodically we read some of these memory information like top 10 clerks or top 10 memory objects. And
sorry, Amit, I think your video is frozen, and so is your screen.
There we go.
There we go. Yep. Yeah? Screen's working fine now. Sorry. Yep. Just wanted to double check.
Yes, absolutely. Yeah. I'll try to turn on the video in a while, Andrew. Thanks. Right, and that is where it is important that you as a DBA developer, if you're really troubleshooting SQL Server memory, it is important that you maintain your own baseline so that you can go back in time and check this information. And this is a very classic example that I just showed you now. Like the moment the workload is stopped, SQL reservation clerk deallocates all the memory, and you have nowhere to track that. Okay, just a few seconds back, about 1 GB was being consumed by which clerk. Well, with this, let's close this one and let's keep the helpers on, and I will close one_memory, and let's cause an out of memory exception. So in this first example, and causing an OM exception is not a big deal, but as I said earlier, do not try to do this with your stable systems where you're working and practicing, maybe some dummy VMs. So first I will show advanced options and let's see how much memory is being consumed now, 1539. So I need to restart SQL Server here just to set it back to a low consumption. Okay, I've just switched on to the default camera of the laptop. Fair enough. Okay, so we turn on the advanced option. So setting max server memory is still an advanced option. And let's turn on the helper memory. So now you can see that SQL Server is consuming about 500 MB. What I am going to do as part of this demo is change this max memory to 700 MB. And there is a reason why I am doing that is to cause an out of memory exception. So right now the VM has about 16 GB and I just do not want to stress it so much up to 16 GB. So let's do this with 700 MB. That's what it is set with. Let's open the second file, troubleshoot SQL. And what we are going to do here is right now, if we run this, and I'm just showing you physical memory is about 465. I'm looking at all the memory objects now, DemOS memory objects, and order by total MB descending. So I'm trying to see all the memory objects. I am seeing all the memory clerks. And there is a reason why I'm running these queries, because as memory gets consumed and when I start getting OM exception, I want to track dynamically which clerk or which objects were causing issues. So when I run this, I can see everything is very quiescent right now, all good. 467 is where we are sitting at, and 700 is our target memory. So anything goes beyond 700, remember, it can overcommit a bit, but maybe not more than 800 MB, and then we will start getting errors. Now, cause OOM is the batch file that I'm going to run, and it's actually going to cause om.sql. It's going to call this SQL file, which is doing something, and I will show that to you after the demo is done. And if you are recreating this, I have put the steps in readme.txt file. Okay, with this, friends, let's cause om.cmd. So we run this. And let's go back into troubleshooting and we'll see. Now you can see that physical memory is being consumed. And if I keep executing this, you will see memory is being increased 557. And you may also observe that a mem object type cursor execution eats up about 100 MB. So something is happening with the cursors there. And what's important to note here is that when you look at the clerk information, so you can see cache store SQL CP, which means that, of course, cursors, memory objects are being created by cache store SQL CP, which is the ad hoc plans, which means these objects, cursor objects, take up their memory or they request memory via cache store SQL CP clerk. Let's execute this. And then you start getting errors. So this says there is insufficient system memory and resource pool default to run this query. Well, this is fine. Let's go and look at what's happening here. And right here, you can see OM errors, and you can see there is insufficient system memory and resource pool default to run this query. So what exactly happened was that we set the max memory to 700 MB, and the batch file was actually opening up cursors, but it wasn't closing it. So there were a lot of orphan cursors at one point crossing 700 MB, and then it hits OM exception. What is interesting to note here is that let's see this workload is now stopped, And when you run the troubleshooting DMB, you can see that physical memory is about 751. As I said, that the consumption could be, it could be overcommit of more than 700 MB, which actually happened, 751. And what is important to note here is memobj. So now there is no cursor information here at all. Now this is interesting. This is very similar to what you saw earlier with SQL reservations clerk. Allocations happen, but the moment the workload dies down or the session is closed, the clerks release the memory. Now this is what exactly happened here, and the reality is in real world, I mean, you may see a few things being printed in the error log, and you will see complete DBCC memory status information, but it becomes very difficult to track down what exactly caused the memory error. So, and this is where the baseline really helps. Let's close this one and open up the next one now. And I will take up one more example of out of memory exception. And this one is going to be a little more interesting. In this one, I'm going to again use clerks and memory objects. So sorry, but for the purpose of the demo, I will have to restart SQL Server once more, because all these demos, I need to just kind of reset them back and forth again. Okay, so while this is starting, let me see if I can fix my primary camera. Looks like Andrew's shoulders were rubbing on. Even his camera didn't work in the beginning. Okay, now it works, looks like. Okay.
Yep, all good here.
Okay, perfect. Thanks, Andrew. So let's look at the helpers DMB now. Where are we? We are at 360 MB, and this is much lesser because max memory is set to 700 MB already. And I'm not going to change this to 700. Let's put it to 600. So we are going to show advanced options. That's already turned on. Set max memory to 600 MB. We have done that. Now 600 MB is max, and we are going to cause another round of memory allocations error. And again, what I'm trying to do here is, again, I'm looking at memory objects and trying to filter, trying to sort on the max consumption of these memory objects, and likewise the clerks. And let's go and execute this. Everything is very quiescent now. You can see physical memory consumption is less than 400 MB. All objects are sitting nice, clerks, all good. Let's cause the memory error using cause.om.sql. And let's execute this. And we'll come back and see what exactly these folks were doing. Okay, there you go. And while this script is running, we go to monitor mem. So what I've done for each demo, I've created a separate monitor mem.sql so that it's easy for you to check. Now, while this is running, look at physical memory consumption. Quite quickly, it will catch up with 600 MB and go slightly beyond. Look at memory object. So that you have a memory object MSXML with current total of 177 MB. And now you know that this is something to do with XML. What is interesting to see here is that XML, for XML allocations, for XML documents or XML fragments, there is no separate clerk. And that memory request happens via memory clerk SQL general. So let's go and execute this. And you can see SQL general is on top there, consuming about close to 200 plus MB, yeah, which is MSXML there. And at some point, we start getting errors. So you can see the OM errors. XML document could not be created because server memory is low. And this is what was expected. Now, friends, if you see, if I close this session, at least here it may be a bit of savior. If I execute this, you can see from 200 MB, the memory immediately gets truncated down and the objects are cleared off. And now the consumption is only 50 MB. But then you cannot rely on this. The point is in dynamic memory allocations and deallocations, the memory objects can be completely freed up, which means if this example, what I am showing you right now, it happens very similar to what you saw earlier, where when the workload dies off or the session closes, you have absolutely no information to rely on. And that is where your baseline is going to be very helpful, where you can go back in time and understand how memory allocations actually happened, which clerks were on top, which objects were on top, and probably you can correlate and get some information. Otherwise, Otherwise, it really becomes very difficult to troubleshoot SQL Server memory. So I am with about 60 minutes. So one more demo maybe, and then we can jump to questions. So if we go to the last one, 3OOM, and in this, I'm not really causing out of memory errors, but I'm just trying to show you the SQL reservation and the resource semaphore for the query workspace. That is something which is not very popularly known as. And again, a quick background about this. When you have workloads like these, for example, this is a very dummy workload where you are doing a multi-level sort. So expensive sort operations, hash operations, exchange spills in parallel operators, they require extra memory. And this memory is called as query workspace memory. And again, a percentage of the total memory is given to this specific clerk. And again, the memory broker would not just allocate anything and everything that your query plans are asking. You need to kind of go and investigate when there is a wait for memory allocations for these. For example, let's take up this workload. Let me close all of this now for the time being. And what do I do? Set max memory to what's the current memory, which is 599, which is fine. And let's put this to 1000. Let's set this up here to 1000 for the purpose of demo and hope it works. And then what I am going to do is open up resource semaphore wait type. And let's close this, and we have the helpers. And I'm going to add 10 users by calling this workload. So let's get started and let's go back there. And now you can see here, memory grants outstanding and memory grants pending. This means that 2 instances of the queries were actually were given memory, and there are 4 queries that are actually waiting. And if I run another instance of, so I say 10 users, but it's actually calling this 5 times. And now if you go here again, now you can see that grants pending has now turned to 10, which means memory grants are pending for this particular set of workloads. And if you run the waiting tasks DMV and filter on wait type resource semaphore, and let's only do this much, and another helper DMV called dim exec query memory grants, you will get some information. So now you can see that so many different workloads are waiting on resource semaphore. So when your query, which has all these expensive iterators that are asking for extra memory, are waiting on memory grant, they wait on type resource semaphore. And using the memory grant DMV, you can actually find out which sessions and whether they have been granted memory or are they waiting. So if they have been granted memory, they have a grant time, or else the value is null, which means they are waiting. And how much memory are they asking for? Each of these instances are asking close to 184 MB. That's what is really happening. And you can also track this using the perfmon counter, memory grant pending 10 and outstanding with 2, because only 2 instances have been granted memory. If you look at the helpers DMV now at this point, let's go and execute. We anyway cannot go beyond 1000 or so what we have allocated. And you can see memory clerk SQL reservations is sitting right at top. SQL reservations clerk triggers in to reserve an advanced amount of memory for this query workspace. And that's why this is called as reservations. If we close all the workloads now, let's stop all the workloads. And that's what we did earlier as well. And if we go back to the helpers DMV, and you can see we are back to the quasi mode. Reservations have deallocated the memory. If you go and look at the perfmon counter there now, you can see page life expectancy was something with like 5,000 numbers, but it got reset a couple of times when there were memory pressures and errors. And now memory grants outstanding and pending are all at 0. So this was dynamic memory allocations. At some point, what happens is if you have too many queries, again, waiting for resource semaphore, they may time out. But then I think the timeout value is 24 hours or something. Somewhere it's documented in internals. Well, big number there. That's how it is.
Speaking with this timeout values, I have to slowly take a look at the clock because we're already 5 minutes over.
Okay. That's with this, friends.
Amit,
I think
you've got until the next session is at quarter to 4 UTC, and we've scheduled you in until 3:30. So you got plenty of time.
That is correct, but Amit was mentioning that he wanted like 15 minutes for Q&A.
Yes, yeah, but I was just saying because we've had some interruptions, he's got plenty of time, so it's no problem.
Yeah, all good.
Right. Thank you, gentlemen, for pitching in. Well, I guess I've completed all the demos. So we completed the internals, the out of memory error 1, 2, and 3. So I think we're all good. Maybe I can just go back and summarize, and I'm hoping for a lot of questions to come in. And now Ben and myself need to get active with the questions. So let me just share back the screen 3. There you go. With the slide. All right, friends. With second. With this, we come to an end of all the demos, and yeah, here is a quick summary. So the whole idea of this session was to kind of talk briefly about the architecture and show you how SQL Server memory works and how to approach troubleshooting. Sorry for a bit of hiccups, but thankfully all the demos worked, and that was most important. If you have feedback, yes, Andrew shared the feedback link, which is 8KB online/feedback, if I'm not wrong. And we are on Twitter, _Bansal. I saw a few folks tagging 8KB as @8KB. It's not @8KB, it's @8KB conference, so CONF. So if you have feedback, please use our Twitter handles. Time for Q&A. So let's see, Ben, if we have questions and we can get started.
Please. Oh, we have a ton of questions from the Brain Fried audience. So first of all, thank you very much, Amit. First question is coming from Max. So his question is, how should we configure VMware guest SQL servers for optimal NUMA configuration? So even though the VM is configured to have 4 sockets, SQL only sees 1 NUMA node. Is there a guide for SQL servers for that?
This question is from Ben?
From Max.
Max. Hi, Max. I'm not a specialist on VMs per se, but I think memory architecture of SQL works exactly the same way in VMs as well. But what we need to take care of is hypervisor specific best practices, whether it is Hyper-V or VMware. And I know there are certain ballooning concepts, etc. Like in Hyper-V, I know that how you can show up sockets and NUMA nodes and how you can reconfigure it for SQL Server at the hypervisor layer. I'm not sure if there is any known white paper or Microsoft architectural guide around it, but there are some experts in the community like Joey who do a lot of work on VMs. Maybe they might be able to help. If you can post this question with #SQL help, I'll certainly follow this up.
Perfect. And our next question is from Sean. So Sean has a server where sysdm OS memory nodes lists 4 nodes, and virtual address space reserved KB is 1343 gigs, so 1.3 terabytes for 2 nodes and 0 for the other 2 nodes. What is the significance of this difference?
If you have 4 nodes being configured and for 2 of them it's showing up to like 1+ TB for both of them, and the other 2 it shows up nothing, which means those NUMA nodes may not be in use or may not be configured, which means there could be a possibility that soft NUMA has been implemented to reconfigure NUMA nodes. That's what it means. 0 as a value would mean that those 2 NUMA nodes are not in use.
Excellent. And next question is coming from Arthur. Are there any rules that set priorities for one of the memory clerk over another when they compete for memory?
So memory broker does that job. I have never read or heard about memory clerks gaining priority one over the other. I think it's very dynamic algorithm, and the broker does the job of managing the demand supply. So to my best knowledge, I think the answer to this is no. I don't think that there's no prioritization here.
Okay. And next one is an easy one from Bjarke. I hope I'm saying that right. You were mentioning heap leak DLL. Is heap leak DLL something you wrote? Is that something open sourced, or so basically the question is, can the source code of heap leak DLL be made available?
Yeah, of course I will make the source code. It's a simple C++ DLL with I think the new function and the malloc API to just kind of eat up Windows memory. Bad DLL, by the way.
When it comes to me, there's nothing like simple C++, but because C++ always is melting my brain. Roman has a question. How do you detect a potential memory leak, specifically with the case of creating a clustered column store index?
Come again, Ben, once more, please.
So with the special case when he's creating a clustered column store index, is there a way to detect potential memory leaks happening there?
No idea about clustered column store memory leaks. Sorry.
All right.
No answer to this one.
Then we have Fabiano. Is all memory reserved for a query allocated when the query is run, or is it reserved and only allocated as needed? So for example, you have a query that has a gigabyte of memory grant, but it only uses 10 megabytes. Will SQL Server allocate that gigabyte that it's been granted, or only those 10 megabytes that it reserved?
Okay, so the reservation happens upfront. That's what I have seen, which is when the query optimizer is actually compiling the plan and it has the plan with it even before executing it, it knows the amount of memory it needs. That may not be always accurate, and that is why in latest versions of SQL Server like 19, we have these adjustments being made right in the second execution. So yes, the answer to that is the reservation will happen upfront, and it may be that it uses much lesser or much more, which it can recorrect in subsequent execution. But in first execution, it will use what was reserved.
Okay. Next question is coming from Rakesh, and it's about a specific weight type. So how would you troubleshoot the resource semaphore query compile weight?
Resource semaphore query compile weight does not pop up so often, but yeah, we just have to look at the query itself. It might be a pretty complicated query and is using a lot of compile time memory. That's what I can say. So if you really hit that up, we might have to just look into the T-SQL query there. It could be a complicated query.
Cool. Next question is coming from London DBA. So direct window memory allocation should be exceptional issues for most standard SQL servers. So maybe it's actually more a statement than a question from what it looks like. I'm gonna and then maybe you could see if you agree or not. So I'm reading the whole thing to you, sorry. Direct window memory allocation should be exceptional issue for most standard SQL servers, so ones that don't use extended stored procedures and other fringe SQL features. That's a statement that you would agree to, that direct window memory allocations should rather be the exception than the norm?
It's difficult to say whether it is direct Windows allocation is an exception, because it's not a best practice to actually run DLLs, out of process DLLs in SQL Server address space, but people do it. So it's not really an exception. Yeah.
Cool. Next question coming from Maria. Is memory governation in SQL Server done at a specific level at a level of specific memory clerks? So can an individual memory clerk cause an out of memory exception?
Yeah, of course. See, the one specific clerk just does not cause it. You see, all clerks are competing for memory, because in some of these, I would say, engineered demos that I showed you, I was just running one specific type of workload to just cause an OM exception. But in real world, you will have all sorts of queries running and all sorts of clerks competing for memory. So, collectively, anything can just cause an OM exception. And it's like a bunch of things causing an exception, but others becoming a victim. So making a statement that one specific clerk is causing it is not really very realistic.
Okay. So we get a question coming over from the Slack channel from Jay. Can you provide a sample of a good monitor for capturing a baseline?
Yes, of course, I can do that. If someone can, follow up with me. If you can just drop me an email at amit.bansal@sqlmaestros.com. I have a script which I can share with all of you. Yeah, no problem.
Excellent. And while we're talking about baselines, what would you consider the bare minimum metrics that should be collected for baseline memory usage?
Well, that is a difficult question to answer. There are so many metrics out there. So I'll answer it in a different way. When we are thinking about baselining and capturing baseline metrics, I start with the problem. We do not go with a ready list that these are the things we need to capture, because it could be overwhelming. There are so many DMVs, so many numbers to capture. So we'll start with the problem and keep capturing whatever is relevant to fix that problem. And really, one customer's baseline is so different from another customer's baseline, because they might be facing different problems, and we just stop where we see that the problems are getting solved. But yeah, some numbers are common. I mean, of course, you want to capture total usage, and in OS ring buffers, you may want to capture, because that gives the notification for whether physical memory is low or is doing good. You may want to capture waiting tasks if the wait type is resource semaphore, for example. The other gentleman talked about resource semaphore, query compile. You may want to capture that information. Memory grant information you may want to capture. I do capture top 10 clerks, top 10 memory objects, and some of these numbers. So yeah, a bit of these are common across any memory troubleshooting.
Cool. One little thing for our attendees: please do not use the Q&A as a chat substitution. I see a couple of people basically using questions, asking questions, so they pop up as answers to others. This makes it super hard to follow up along. So please use Slack for the chat. A question from Arthur. Again, is max server memory limit, is that divided equally among the NUMA nodes, and can actual workload change that allocation?
Ben, I lost you in between.
So you have max server memory set, you have a max server limit. Is that limit divided equally across the NUMA nodes, and can the workload basically change that allocation, or would they always have the same equal allocation of memory?
Yeah, that's equally divided, and workloads cannot change that. That is a decision which is taken during boot up.
Okay. Another wait type question on resource semaphore. So Brett is wondering, can I create an alert for resource semaphore waits, or would that alert also be waiting for the memory? So would that basically, would that alert never fire, because by the time the alert fires, there's no need for the alert anymore?
No, actually, the idea is creating alerts for resource semaphore may not be a good idea, because it keeps happening all the time on busy systems. When we have a heavy OLTP transactional system and all sorts of sorts and hashing going on, you may actually see a lot of such alerts, because these wait types are very, very short-lived, sometimes like just a few milliseconds. And that's fair, waiting for a few milliseconds to gain access to that extra memory and then you get it is fine. You may not want to be bothered at that time. But if you are asynchronously capturing it, and then from your later analysis, you may want to find out if a particular wait was more than, let's say, a few minutes or something, that is what you may want to go back and investigate.
Okay, Arthur has another question. I don't fully understand it, but maybe you do. Can query memory grant span the NUMA nodes? Arthur, maybe you can clarify that question.
No, I think it will not span the NUMA nodes. Think about this from a NUMA architecture. CPUs need memory. So the threads that are actually executing your workload, is executing your query, is requesting for memory from the specific node. And spanning is how it could actually happen is that if a specific node is choked up with memory, it does not have enough memory to allocate to the thread, it can actually go and ask the other node for memory. So there could be cross pod memory access. In that way, you could say like, it's spanning, but really if you see, it is at the hardware level, which is one node requesting memory from another node. This is called as foreign memory. I think that's the term, yes, foreign memory, when one node consumes memory from another node.
Cool. Another question by London DBA. So if I clear the buffer cache and then I run a select on a big table, would I expect to see high memory on one memory node and 0 on the others? Or would the memory spread equally across all memory nodes? So his guess is the connection is linked to one memory node, so only one memory node would show with the high value?
That is correct.
Okay, and another one from London DBA. So for out of memory for cursors, XML, etc., he'd argue that there's not enough built in monitoring for such features. So you need to be. Okay, it's also more of a statement. And then there is I don't know if we have time for this and if that's something you can pull up that quick. Maybe otherwise you can refer Bjarke to something else here. So because Bjarke is asking for another quick demo. What happens if the host is, or maybe you can just answer it. If the host is under severe paging, what happens with the memory clerks?
If the host is under severe paging, what happens with the clerks? Well, what I think will happen is the SQL Server, overall SQL Server memory is going to get trimmed down in that particular case. So you will probably see that SQL Server is releasing memory back to Windows in case of low notifications being sent. We saw clerks getting trimmed down now as well when there was OM errors. Just for the attendees, on the screen, you have connect with ab@sqlmaestros.com. In case there are more questions that we are not able to answer now, and if you want to shoot up a mail, connect with ab@sqlmaestros.com, or Twitter is also another way. I would be very happy to interact with you on Twitter there. And scripts are up there. And if you need scripts immediately, you can send a mail to connect with AB again. That's what you can do. Or the resources link there, you can bit.ly/SQLmaestros resources. They're all uploaded. And it's also there on 8KB GitHub. Can I request Andrew that I would resend? I will just correct, make a few final changes to readme.txt just so that people can execute these scripts better when they're trying. So please ignore the last zip file that I had sent, and I will resend another one.
That's no problem at all. We can get that changed for you. And I'm pretty sure we capture all the Q&A questions that are asked. So if there are any unanswered ones, we'll distribute them out to the speakers at the end of the event and they can get in touch.
Excellent. There's actually one more question for Mark. Alexei kept following up on, because he asked when the videos would be on YouTube, and I'd say it will take a bit, and he asked me to define a bit, please. So maybe you can clarify that a bit.
That's one for you, Mark.
Over the course of this afternoon.
Oh, so actually, no, this is a good point to bring up. So right now, the live stream is happening on YouTube. When we're done for the day, we'll leave the live stream up of the whole conference until we get it chopped up into the individual videos. So you'll be able to access all of the content like immediately after this is done. But you might have to kind of, scrub through it to find the exact thing you're looking for until we have a chance to get it all chopped up into individual videos.
Cool. Thank you for that, Mark. Thank you so much, Amit. Awesome session. Thank you so much to all the attendees for a whole bunch of questions. Oh, I see another friend showing up there, Mr. Argenis Fernandez.